much. It's my great pleasure to talk on this special occasion for MOL. As his academic nephew, my mathematics is largely influenced by MOL's mathematics. So including those important results, such as the equidistribution theorem of Sheville-Ullmann-Zhang, and the solution of the Mordell conjecture by MOL. Today, my topic is actually related to the Mordell conjecture, also slightly related to the equidistribution theorem. So I will start with the classic ones. So my first part will be the main theorem. I put an S here. So not all theorems are due to me, like just all important theorems related to the subject. OK, so assume K is a number field. Assume X over K is a smooth projective curve. Smooth projective curve. Actually, we also need like geometrically integral, but I will omit it, of genus G. G is greater than 1. And then we have this celebrated Mordell conjecture proved by Faltings. Which simply says the set of rational points of X is finite. OK, so this proved by Faltings in 1983. So I will sketch a little bit. So there are 3 proofs, because we're going to use one of them. So the first one is Faltings, 1983. So Faltings proof has like many original constructions, connections. So the most like important ones to me is his introduction of the Faltings height. Use it to count abelian varieties or curves with fixed ramification set, a better reduction set. And also he connects it to modular space. And also he uses Piaget-Hodge theory. This Hodge-Tate decomposition for Tate module of abelian varieties. So this is the first proof. And then the second proof, which is more related to my talk. This is due to Vojta. It's 1991. And the Vojta's proof is inspired by the proof of the 2-Ziegel-Roth theorem in differential approximation. Differential approximation. And he also uses Arrow-Kalov geometry, uses more, I should say. Faltings also uses some Arrow-Kalov geometry to define Faltings height and to obtain a Northcott property for Faltings height. But Vojta uses like more, like notably, he uses the Riemann-Roch theorem of Gilles and Soleil. Not just the intersection theory, also like arithmetic Riemann-Roch. For 3-dimensional arithmetic varieties, namely like integral models of squares of the curve X. So that's Vojta's proof. We will come back to some consequences of his proof later. And then the third proof is more recent. This is by L.V. Lawrence Venkatesh. So that's 2019. So LV's proof at the beginning overlaps Faltings proof. Convert the counting of points to counting of curves by this Cordero-Paschen construction, and then convert to counting of abelian varieties. But then after that, they reduced the problem to a local p-adic problem. And then the major part of their proof is this p-adic-Hodge theory. Okay. So now the goal today is for this uniform version of the Mordell conjecture, or even quantitative version. So the goal is, we already know it is finite, then we want to bound the number. So how many points are there? Like, of course, we need to use some invariance of x. Now, a breakthrough on this question is due to Vojta.
Is it believed that the height of the points can also be bounded? I don't know in which sense effectively, but it's. I think it is not exactly no. I mean.
Yes, we believe it. That's the effective Mordell conjecture. Roughly, it has many forms, but one form says the height of the points is bounded from the above by the height of, not the height, or even just like by the genus and the discriminant of k, and also by the set of better reductions of x. Maybe we need height, Faltings height of x. Yeah, we do need that, yeah. So okay, so we already here. This is not related to my talk, but this is actually a much more important conjecture. So there are many versions. Now I just write down like a convenient, strong version. So it's for any p in xk, we have this height of p. So of course we need to choose like an ample line bundle. For example, we use the canonical line bundle, and we need to choose some metrics. But then, so this one is bounded by, we need the Faltings height of x, and then we need the discriminant of k. And then we put some constants here, so we put, say, a1g, a2g. a1, a2, I put g here, means they depend only on g.
The degree of k.
If I put dk here, then it might be fine. Or yeah, we have different versions. Yeah. So.
Depends on how you define the height.
Oh, you're right. Whether I normalize it, yeah. So yeah, this is the effective Mordell. So, but this may be too hard. Like, at least like, for the moment, I have no idea about it. Like, okay. So, by the way, in case you don't know, like, this is equivalent to some version of the ABC conjecture. Okay, so now, Vojta, DGH, Dimitrov-Gao-Habegger, and then Kuhne. So for the years, this is 91, this is 91, this is 20. And the theorem says we have a uniform bound, like in terms of some uniform constants, but we also need like the rank of the Jacobian variety. So says xk less than this c of g 1 plus this rank just plus r. So when I write C of G, just like this A1G, A2G, I mean like a constant depending only on G. So this R is the Mordell V rank of the Jacobian variety. Okay, this is a fantastic result. So sort of like to get this result, we need to combine these three results. Before I talk about more about the proof of this. Now I represent the result today, like from me, quantitative quant version. So this is a joint work with Jiawei Yu and Shengxuan Zhou. So Yu. This is not me. This is me. Okay. And then Zhou. So the paper is almost finished. At least like we finally have the final result. So this Jiawei, this Shengxuan. Okay, so this is YYZ. So yesterday, like Zhou and me talk about like today, like our talk. The first three talks are given by YZZ. Right? So it's the YZZ, the authors of the book. But now this is not YZZ, it's YYZ. So then I realized that like actually we always like somehow have a common sense that Chinese names are really modest in alphabetical order. except this guy. Okay, now what's the theorem? So basically, we want explicit expression of CG. Like it's in terms of G, so we write it down. Okay, so it consists of two parts. So this is like the coefficient, this is the base, and it's really like explicit. So you can think this is like this, we have like 1 plus R. So you write it as like CG to the R, or maybe C1G, C2G, then it matches the form. And these two constants have different reasons. They're really like from different computations arguments. So as you can imagine, so this constant, we call it a Manning-Mumford constant. So as it's related to the Manning-Mumford conjecture, if you only consider torsion points, then you can ignore their parts. So this like gives a bundle of torsion points of X by embedding X into the Jacobian in some way, by this Abel Jacobian map. And then this constant, this exponential bound, this constant comes from Vojta's inequality. So we call it Vojta's constant, Vojta constant. Okay, and this constant looks very large, the 10 to the 16. And of course it has like room, really has room to improve.
So the previous proofs are not effective?
Sorry?
The previous work that you quoted.
I will explain sort of like this combination is not. But we will have more proofs and eventually like we will have 3 proofs. I will go to that. So, and then a remark. This is to emphasize that this base, this Vojta's constant, goes to 1 as g goes to infinity. So this somehow says like this exponential boundary is not that bad. And this is like this is a conjecture expected by Dimitrov-Gao and Habegger. The expectation is from Vojta's inequality.
Excuse me, do you have the same bound for the number of points in a given subgroup of rank R?
Yes. Yes. So yeah, I was a little bit of lazy, so I didn't write it. So it's xk. If we intersect a finite generative subgroup, only a subgroup of finite rank.
K bar.
Yeah, K bar. So this is in J of K bar, and then we will have the same bound. Okay. So that's about the Vojta's constant, the base of the exponential. And then Ziyang told me that there is a very interesting consequence of the theorem. So the corollary is about like we want to take average of the number of points. But in general, it's hard to take average of the exponential of the rank. But in one case, this is by the work of Bagava and Gross. I first write down the corollary, or maybe I first write down the theorem, since I already started talking about the theorem. So their theorem says we average the Stemmer group of hyperelliptic curves. So originally, of course, it's well known that Bagava computed like average for elliptic curves, but actually then they can compute average for hyperelliptic curves. So let X be a hyperelliptic curve of genus G greater than 1, and then with a over Q. With a rational Weierstrass point all this just means we can use the affine equation, the well-known equation, the equation of this form, this y squared equals fx. And then fx is a polynomial in x of degree 2g plus 1. So this rational Weierstrass points becomes the infinity here. Okay, so they need to work on the equation. So that's the reason for their assumption. And then the statement says the average of the Stemmer group, two Stemmer group of the Jacobian. So J always represents the Jacobian as in here. So the average of the two Stemmer of the Jacobian is equal to 3. So this average, we have infinite many, of course, infinite many curves here, so we need to order by height, or more precisely by Faltings height. Or if you are not familiar with this, you can think it's just ordered by the height of the coefficients. So we already have equations. We have coefficients, just like this Weierstrass equation for elliptic curves, and then we just count the height like of their coefficients. Okay, now if we apply this marvelous result to this one, so then this two-Semmer group, we have this trivial bond, trivial effect. This two-Semmer group is less than or equal to 2 to the r. This two-Semmer group, greater than or equal to average size. Because the Semmer group, the weak Mordell V group maps to the Semmer group, so we have this. Now, then as long as this 1 plus 4 over root of g is greater than less than 2, then we can apply the bond. So now the consequence is if so x is still x over q is still hyperelliptic as above, like this in Bagava-Gross theorem. And then now we assume that g is greater than 16, so that the base is, the Vojta constant is less than or equal to 2. Then we get this average of the number of points. Now we take the average. Now we change this one by the Semmer group, and the average gives 3. Okay, so that is the corollary. So somehow, for example, that's like also like another conjecture, folklore conjecture, maybe less striking than this, saying that like this set is bounded in terms of k. Oh, this over q.
Sorry, and this is an average over all hyperelliptics. I mean, all the x's that satisfy your Bagava-Gross.
Yeah. So maybe I put here. So these are not my major concern, but they're related. So it's this xk. There's a strong bond conjecturally. This is given by only the degree and the genus. Okay, this bond is a consequence of the Bomberi-Lang conjecture by the work of Caparezza, Harris, and Mazur. So if you believe Bomberi-Lang, then you believe this. Okay, so this is sort of like a weak evidence of that. At least like the average is bounded. Okay.
Strong conjecture is average should be trivial. I mean, probably just 1 point, right? Weierstrass points. Why not 1?
So a related result by Pullman and Zhou, they say like there's a positive ratio of x such that it only has 1 point, only has like this rational Weierstrass point, just a positive percentage. Like the percentage depends on g, but when g goes to infinity, the percentage goes to 1.
Oh, I see. I have G there.
Yeah, you're depending on G. But their work is also based on this bound, so it's just like they use Chabot method. So once you have this, then you can get like a positive proportion of X such that the Mordell weight rank is less than the genus. Then you can use Chabot's method to bound the points. Okay, so that's like the first part of the talk. So a remark is that this constant can be improved significantly. Even we can break down this constant to 100 or something, and this G to the 7 can become like G to the 3 or 4. Okay, so that's the first part of the talk. I can also use this. Right, okay. So now, the second part is this uniform Mordell. So this is sort of like the, we'll first look at this non-effective version. So right here, so this xg is less than cg 1 plus r. Okay, so the idea of the proof is to combine two different bounds. One bound is for like the large points, like points of large height, and another is like small height. So first we need to take a point or whatever. Let's take a point or like a divisor. Take a point in xk or xk bar. Let's assume it has a rational point, and then we take this Albert-Jacobi map. So this map, we use P as the base point. And then we have the Laurentide height. We take the Laurentide height on the Jacobian and then induced by X. So I'll write them together. X goes to J, goes to R. This is my H hat. So here is X goes to X minus P, goes to height of X minus P. Now, the idea is to combine the bounds on large points and the bounds on small points. So the large points is due to Vojta. So the bound is now for here I just write roughly as x in xk when the height of x is greater than something, and then we want it to be less than something. This is sk. This is obtained in Vojta's proof of the Mordell conjecture, the second proof of the Mordell conjecture. And this implies the Mordell conjecture, because when the height is small, there are only finitely many such points by this Northcott property. So this is for large points. And then for this small points, this is DGH and Kuhne. So then it's I need to write x minus p here. And then we combine them. So now this one is uniform Bogomolov conjecture.
The question mark should be the same.
Actually, in practice, they are not the same, and they don't cover the whole thing, and you need to use some sphere packing, some extra trick. But those are like sort of elementary. Okay, so for this Bogomolov conjecture, so can you see? Maybe you can see this. This is too dark. Rather. Not high enough. Forget it. Okay, so so let's recall the Bogomolov conjecture. Proved by MOL, this theorem. This is in 1998. So it's just the setting, but I write it seriously. So suppose x over k are given, and then this g is greater than 1 as before. Now this is for fixed x. Now then says we're also given one more thing. Say p in xk bar, given a point, and then there exists a constant epsilon greater than 0, such that this is the number of points x in xk bar, and then the height of x minus p. This is the height in the Jacobian, and then less than epsilon is finite. So this is the original Bogomolov conjecture, and then I put some remarks. First is this proof uses the equidistribution theorem. Used equidistribution theorem of Shapiro-Ullmann-Zhang. That's maybe 96 or 97. And then Zhou Zhang extended to high-dimensional case, subvarieties of abelian varieties. Okay, so now we are going to consider a uniform version of Ullmann's theorem. This uniform version we can imagine. So we want this constant epsilon to be uniform, and also this infinity. Infinity means a finite number here because it's less than. Let's put it delta. So we want these two uniform. So then this uniform version So we have constant C1G, and then I will put it's related to the Faltings height. and then plus height of P minus so now this is sort of the epsilon, this sort of the delta. Of course, there exists C1g, C2g such that this is true for all x over K, genus G. So now this part is like extra term. So this extra term is right here. So so first DGH K together the original theorem without extra term, and then me. That's also in the same year with every extra term. So when I obtained this result, like my extra term is like comes out like naturally from like my proof. Our proofs are sort of very different. I don't have much time to explain those two proofs, so I will not explain. But I will explain the third proof later. But then when I got this extra term, I wondered like how do we use it? Like, is it useful? Because this makes the theorem stronger. And then now it turns out that yes, we can use it. We use it to get better constants, like get this Vojta constant going to 1 as you go to infinity. So now the third proof is the proof I want to mention. So this over function field. Suppose K is a function field, and we can like propose the same question, the same answer. Maybe our same X is long as a trivial. Now over function field, this by LSW, L looper, S is Silverman, W is Williams. So this is still 21. So that year is sort of like is for uniform Mordell. Okay, so now over function field, they get this bound without the extra term. But the most important thing to us is like they have explicit constants. So and the explicit C1, C2. But over function field, and these two like we don't get explicit constants. So this DGHK proof, DH proved like a slightly weaker version of that one, and Kuhne used the equal distribution, like a generalization of this SUZ equal distribution to quasi-projective varieties, and then that argument is sort of non-effective, and my proof is sort of effective. I use the bigness. I need to find a small section, but it's really complicated to get a constant. But LSW's method is really good for explicit constants. And also another difference is these two like these two proofs worked on modular space of curves, but this proof works on a single curve instead of modular space. So a single curve and estimate and get the constants.
Can I ask a question? So in the initial proof, epsilon was something like omega squared divided by something. And you couldn't take twice this number. So how do you relate the omega square?
Omega square is like a it's like another proof. You mean like proof omega square is greater than 0 to get this?
Yeah, but you could take epsilon for omega squared divided by 2g minus 2 or 2 times 2. I don't remember exactly, but you couldn't take, you knew that there were infinitely many points in k bar with This side.
You compared omega square and Faltings height.
Oh, you mean this? Oh, yeah. Yeah, it's about this. So, yeah, I never explained this. So this is like max of H Faltings height of the Jacobian, and 1. We make it greater than 1, greater than or equal to 1. So this Faltings height is just a usual Faltings height of abelian varieties. And then here's like a little theorem. That's also due to me. So in the same paper for this uniform Bogomolov says this Faltings height and this omega square bounded each other. So I put C3, C2, C3, C4. So this omega x bar, omega x, and then we put this admissible metric. So this use John's admissible adelic matrix. And if you're not familiar with this, so you just think if, in the case if x over k has good reduction, so you have, so that you have x over k, this projective smooth, then this omega x, this is sort of equivalent to, you use the usual omega x over OK, and with the Arakelov metric at infinity. When we have better reduction, Zhou defined like metrics at non-Archimedean places analogous to the Arakelov metric. Okay, so then, yeah, this is also important. Like, so then in the uniform model, uniform Bogomolov, like we can switch these two constants, either omega square or the positive Faltings height. And also, actually, in the purpose here, or even in many other purposes, this is a better invariant than this one. Okay, where are we? I talked about this, and then the theorem. Yeah. Okay, so now I'm gonna talk about like the third part. So third part, this quantitative version. So so now we need to get like explicit constants in all those estimates. So there are two major ones in here and here. So these two. So we get like, so, oh, my bad. I just confused myself. Okay. So this explicit constant, I don't have time to write down the formulas, but I just write it in English. In Vojta's inequality. So it's sort of like you have this C1G, C2G, whatever, and those are like explicit. So in our expressions, all these functions in G are power functions. And then also explicit constant in this, let's just say explicit constant for number field version of the proof of LSW. So this is like the third proof. So they did it for function field. They didn't do it for number field. For number field, the major abstraction was really some. There are actually a few like bounds, Archimedean bounds. So all these difficulties after LSW are like Archimedean, just complex analysis. Like we need to bound like a lot of invariants, Archimedean invariants. Those are like invariants of compact Riemann surfaces, inequalities. And then our major innovation is to work out all those Archimedean inequalities for this method. And also it also takes some efforts to get like explicit constants in Vojta's inequality. So now I'm gonna explain a little bit like the proof. I will start with LSW's proof. So
so your theorem is like working not on modular space. It's like working on one curve.
Yeah. Yes. On one curve. Work on a single curve. Okay, so I'll start with like, so X is over K, genus G, greater than 1. And then we need this omega bar. This is still this admissible. John's admissible canonical bundle. And then for any point P in xk bar xk, we also take this P bar, this is P, and then we put a Green function G of P at all places. So this is also admissible. It's still like in the same framework. So this is admissible adelic divisor. Again, if you're not familiar with this, you just assume X has good reduction. And then if X has good reduction everywhere, then you have this. This is like omega bar. And then this one is like you just take the Zersi closure. And then this one, like then you only need to take like the Arrow-Kalov Green function at Archimedean places. Okay, so now.
Sorry. What are the subscripts next to the P and outside?
V is like places. So this sort of like we need to take Green's functions at all places.
So in the places of good reduction, do you have some Green function?
Yes, yes, yes. If you think about good reduction, then you only need the Green function at infinity. And then this part you replace it by the section on the integral model. Okay, and then we have two nice results here. So first we have this adjunction formula. So the good reduction case, like the original case, is due to Arrow-Kalov, and then extended to the current case by Zhang. So this gives this P dot P. When we do arithmetic intersection, this is negative omega dot P. You can put a bar here or not. That doesn't affect it. So And then we have this Hodge index. This, the original version is due to Faltings and Realjack. So now, so here let me just put the easy version. H hat of P minus Q. Suppose we have 2 points. And then we get -½ and then P bar minus Q bar square. This square is intersection. This self-intersection. Now, now we suppose we have n, there is like n points, say P1 up to Pn in xk bar xk. And we want to prove like one of them, at least one of the height is big if n is big. So this is sort of like the a version of the uniform Bogomolov. So we can't have too many points with big heights. So now it suffices to prove a bound like this. So we do this summation of height of pi minus pj. This I is not equal to j. We want this one to be big. If all these are small, then this is small because it's a quadratic. So we want that one is big. This is like the method. This is LSW's method. Okay. That board is important for my yeah, maybe you're right. I still have those boards. So now, now we need to do this one. So this I is not equal to j, and then we use this. We can convert it to arithmetic intersection. Then everywhere we have arithmetic intersection. So okay, and then we need to complete the square now here in some form. And so we also use this type of result. Sometimes this is weird. This is a square, but it's linear. So you have like more choices. But eventually we get this summation I is not equal to j pi pj plus I have constants here. This let me just write roughly because there are some constants, but when n is large, those constants are sort of like this two. some constants. Okay, we have those three positive constants. They are in terms of n and g, and then those constants are, all three constants are positive, and then now this is already like a positive non-negative. So we want an lower bound. So this is already okay, good now. And then now we want to bound these two together actually. So now, then this summation, note, this pi dot pj, this intersection I is not equal to j, this is going to be a summation of all the Green's functions at all places. Is this one. And then now, the second one is this omega square is already greater than or equal to 0. This omega bar is nef, but we want more. We want that one somehow to dominate this one. This one can be negative. We need a result of this type. This g minus 1, 2g plus 1. This phi of x. So this phi is the phi invariant. This is John's phi invariant. And this phi invariant, I don't have time to introduce it, but maybe in Zhou's talk, he will mention a little bit about this. It's related to his talk. But then the most important thing for us is this is local. This is like sum over places. So this is local. So then you see, we want to combine these two terms, but then this is a sum of local. This is also a sum of local. Oh, I need to mention this. This is by many works. Robin de Jong and also Wimt. So now, then the problem becomes local. We want to, for every place V, we want to do like this one combine this one. We want to get a lower bound. So we want to do a summation of G, V, Pi, Pj, I not equal to J, plus some constant here, and then this phi V x greater than or equal to 0. So for every place. And then this like, if V is non-Archimedean, this is by graph theory. This is essentially due to sinker. And then some extra work is LSW. And then V is Archimedean. This is YYZ. This time it's YYZ, not YZZ. Okay.
Wait, sorry, just to clarify, you really just need non-negative? I thought you were trying to show that the sum was larger than some...
Yeah, so this constant is related to this C2, to this C1G. Yeah, so depending on...
You're just saying greater than or equal to 0, or you...
Okay, let's put...
Oh, there is something there that you want to...
Actually, we can get, in the middle, we still have some other constants, or we can save a little bit of this omega, like a power of omega, a multiple of omega squared to
make it even bigger.
Yeah. So I don't have much time, but I just want to mention one thing. Since inspired by Philip and Laura, like they had beautiful pictures, so graphs. So to explain like our complex analysis, I want to draw a picture and then I will stop. So the picture, like sort of like how do we get such a complex analytic bond? So so these two terms are very different. Like you're not supposed to combine them. I think like you can combine them only because they are real numbers. So so the estimates are really separate. Like we estimate that one lower bound, this one lower bound, and but we need to get lower bound by another invariant, like another invariant. And turns out this is the invariant I want to talk about. So suppose X is a compact Riemann surface. So this is like our Archimedean setting. And then the invariant is this Sx, this systole. So this is the length of the shortest closed geodesic of X under this hyperbolic metric. Of scalar curvature -1. So this turns out to be like a very good invariant. And then the thing is, suppose X is in the modular space Mg, and then this is a function on Mg. Then what we have is, for example, we have this phi invariant. Phi X goes to infinity as X goes to boundary. And then this Sx goes to 0 as X goes to boundary. So, and then, of course, then 1 over Sx is like a good invariant, like it block at the boundary. So now 1 over Sx goes to infinity. And then now then we bound each term by this multiple of this one. Sorry, I'll finish my picture and then, okay. And then for this Sx, for the picture, I'll draw like a Riemann surface of genus 2. And then this Sx might be like in some situations, it's like the length of this loop. The length of that one. And then if you do degeneration, then what you do is sort of you imagine your Riemann surface goes to the boundary, goes to the compactification of Mg, and then this one will get shorter and shorter. This Ss goes to 0, so it sort of becomes something like this. Ss goes to 0. And then when it's 0, you sort of like pinch it to one point, and then it becomes a singular curve. Okay, so this is like the invariant. Okay, thank you very much.
Thank you for your talk. Perhaps we do only one question, if there are any.
So in fact, also another proof of Bogomolov without a solution. Just
for single curves? Yeah, for single curves, this is already in here. So by Zhang de Jong, even before Williams, because like use a little bit of graph theory to just Zhang de Jong and the graph theory by Sinker to get like non-Archimedean place to be greater than or equal to 0. And for Archimedean place greater than 0 is by Zhang. So this is already like another proof of Bogomolov.
Okay, because I remember that when we have the prediction everywhere, we still needed something at infinity of this kind. And okay, so this was done after.
Yes, yes, yes.
So perhaps, the last one.
Okay, I just want to ask a very quick question. You can say a yes or no. So do you have a quantitative version of L-kit somewhere in this?
Yes, yes, we do need, yeah. Yeah.
Let us thank the speaker again.
Thank you.